Okay, so now we're going to model drag force, and so what we're going to do is we're going to create some shape here, and then when our balls move through that shape, it's going to apply drag, and then so it's kind of similar to the example in Nature of Code where the balls fall into the water, and once they're in the liquid, drag is applied to them. We're not going to we can make a thing of liquid down here if we want to, but I thought it'd just be a little bit more interesting if we just kind of made a random shape here and called it a force field. So when it goes through that force field, it slows down, and then when it when it's not in that force field, there's going to be no drag applied to it. So let's change the number of movers down to 5. Let's change the time down to 400. And we're going to make a force field. And we're going to make a surface and pass that surface into the force field. So let's do that really quickly. We're going to make a sphere, and I'm going to scale that down. And I guess I can scale it out. Okay, so that's our force field. And so we need to address our how to make drag here. And so I wrote this in, so I didn't need to worry about thinking of the equation. And so here we have -1 times unit velocity. This code is really similar to what we had down here in friction. So let's just let's copy and paste this up. Let's copy this whole thing. Okay, and I'm just going to leave it indented over because we're going to go put it back down there once we have it figured out. So, so this line of code takes care of this right here, and then for the magnitude that we want, we need speed times strength. And so let's make speed real quick. Speed is going to be equal to rs dot vector length of our m dot velocity, and then strength of our drag is, let's just say 0.9, and then if that value is weird, we can change it. And so the length that we want is equal to speed times strength. We're not gonna make this friction now. We're gonna call it drag. So apply force drag, and the length that we want is L length. So speed times strength, that's this right here, and this is the vector. This is the vector that we want, and this is the magnitude that we want. So here's our vector, and then we know that this is unitized from up here, and it's reversed, so it's this right here, and to get a magnitude of this, we're scaling it. So v times length, or v scaled by length. So there's our drag. We're going to copy that and paste it back down in here. Delete out our friction. And when we apply this, we want to apply this only when it's inside of our force field. So we're going to say F rs dot is point in surface, and for object ID we're going to say force field because that's the value that we passed in, and for point we're going to say m dot position. So we need to tab this over. And we should probably put that there. Let's test this. So you can see when it's moving through our force field, it moves slower, especially with this small ball. So we can play around with this and you can see that the drag force that we applied for the speed is so much that it bounces back up, so that would be considered a bug. We're not going to worry about it though. Okay, so we're only looking at it in the first few moments, so let's bump this down to 90, and we can bump this up and look at a lot more. And I'm just kind of I'm going to start now worrying more and more about how much information we're asking this to process, because we're up to 2 seconds right now, which isn't really a big deal, but I just want to keep my eye on that so we don't bug it out too bad. So I don't know how well that's coming across in the recording, but it's pretty clear that they slow down when they're moving through the force field that we created. And I'm going to slide this over. That way yeah, so you can see that half of them, the half that are going through the force field, slow down when they are. And so if you want to think about this like for the water example, so it's like they're going through the water. So that's that example, and then let's move on.